Okay, so in this video we're going to go through some of the conversion problems. We can go ahead and start with number 2 since number 1 was correct. And in number 2 we have 47.32 micrograms. I'll put that over 1. And we want to convert this into meters. Sorry, not micrograms, micrometers. We want to convert this into meters. So this one's pretty straightforward, because all you need to do is go to that blue chart where it has the Greek letters and the prefixes, and you want to find the one that corresponds to micro, right, which is mu, lowercase Greek letter mu. And you'll see that it says 10 to the power of negative 6. So what that means is if you're going to convert this into meters, it's saying that there are 10 to the power of 6 micrometers in 1 meter. So that's why it's got a negative exponent. So I'm going to put it right here actually. 10 to the power of 6. I'm going to use a positive exponent because it's in the denominator. And this is micrometers. And this is for 1 meter. Okay? So once we write that, then all we need to do is, of course, cancel our units. This one was pretty straightforward. And then simplify the fraction. So this is 47.32. And then we're multiplying this by 10 to the negative 6. And then we have our units, which is meters. Okay? And then, of course, we want to put this in proper scientific notation, right? So I'm going to go ahead and move this decimal. It's going to go to the left 1 spot. So that's going to now be 4.732, and then times 10. Now be careful here, I'm moving from right to left, so that turns into negative 5. And then this is in meters. And that represents, the conversion, right? We've just converted micrometers into meters. So remember, micrometers are super tiny. So 47.32 micrometers is, again, super tiny. So that's why it's got this negative exponent in meters, right? 10 to the power of negative 5. So just be careful with this last step, right? So you write the number like that, and then you rewrite it in proper scientific notation. And I would recommend you ask the instructor about the scientific notation. It's probably better to write it in scientific notation, but you can go ahead and ask just to be sure, right? So the next one, number 3, so that we have 83 centigrams, so that's Cg, and we want to convert this to nanograms. So I'm going to try and keep this simple. And to keep it simple, what I mean is I'm going to try and match up the units so that we can cancel them nice and easy, right? So this is centigrams, then I'll put centigrams in the denominator here. And we want to know how many centigrams are in 1 gram. So we go to our blue chart in the picture, and we try and find where centi is. And we see that it's 10 to the negative 2. That means, of course, it's going to be in the denominator, and I'm going to write it as 10 squared. Again, what's important is that you understand what this means, right? This is called a conversion factor. This means that you have 10 to the power of 2 centigrams per each gram. So 100, basically, right? 10 squared is 100. So 10 squared centigrams for every gram. Alright, so that's kind of the main idea here. Make sure you understand what the conversion factor is telling you. So now we can cancel out these units here. And then we're in grams, but we want to go into nanograms. So now we need to write the next conversion. And so I'll put here grams. And we'll say 1 gram is how many nanograms. Let's figure that out. So we have to go back to our chart, the blue one, and we're going to look for nano, and you're going to see it says 10 to the power of negative 9. So I'm going to put it here, 10 to the power of 9, and then ng. So again, we're canceling out our units, right? So we want to go, we're starting from centigrams, and we're ending up with something a lot smaller from centigrams to nanograms. What that means is that our number is going to be actually a lot larger, right? So now all we need to do is just cancel things out. This is 10 squared, this is 10 to the 9th. Oh, well, let me cancel out grams first. Okay. Now this is 10 squared, this is 10 to the 9th. So we can use our exponent rules to cancel that out. And we're left with 83 multiplied by 987, 10 to the power of 7 nanograms. Okay? So what's important again is, let's go ahead and write it in the proper scientific notation. So this is 83, we're going to move the decimal one place like that. So that turns into 8.3, and then times 10, and then be careful because we're moving from right to left. So we're going to be increasing the number. So this is, if that was 7, that becomes 10 to the 8th nanograms. And I'm going to go ahead and leave it in proper scientific notation. Of course, you can ask the instructor about conventions for scientific notation. And then we can look at number 4. And that one has 14 kilometers. And we want to convert to millimeters. So again, 14 over 1 times, we want kilometers in the denominator, so I'm going to put here 1 kilometer. And again, what I'm trying to write here is the conversion factor. So we know, you can go to your blue chart, 1 kilometer is basically 10 cubed meters, 1,000 meters, right? 10 cubed is 10 times 10 times 10. And then we can cancel out our units here. And then now we want to go to millimeters. So I'm going to put meters in the denominator. And then we want to know, okay, 1 meter is how many millimeters? Well, again, you can go to the blue chart and look it up. And we're going to write here, it's 1,000, right? So again, we're going to put another 10 cubed, because that represents the 1,000, right? 10 times 10 times 10. So be careful here, because this, remember, 1 kilometer is 1,000 meters, and 1 meter is 1,000 millimeters. So just be careful with that when you're looking at it. It might seem kind of awkward at first. So now the meters cancels with the meters, and all we need to do is just simplify the math. I'm going to be using the algebra rules, right? Algebra rules here. So that turns into 14 times, I should be using the x. And then if this is 10 cubed times 10 cubed, that turns into 10 to the power of 6. And then if you want to write it in proper scientific notation, you can go ahead and do so. We can move a decimal from here one place. So that turns into 1.4 times 10 to the power of 7. Numbers are increasing as you move from right to left. Okay, and then units is a millimeter, so you can put that. And then you can always check your answer to see if it's reasonable. Check for reasonableness. We're starting with 14 kilometers, and we're converting to millimeters. So 14 kilometers is quite a bit of millimeters. That's a lot of millimeters. You can imagine that. That is quite a bit. So that number is pretty large, right? 1.4 times 10 to the power of 7. Pretty large number. Anyway, we can go ahead and move on to the next one, which is where things get interesting. Because now we have multiple dimensions for the units. So let's see. So here we have 46.2 centimeters cubed. Okay, and we want to go to, hold on, let me adjust this camera. Okay. We want to go to meters cubed. So from centimeters cubed to meters cubed. Okay, so we can go directly and put the over 1 part here. I'm going to go ahead and write this out kind of the long way, just so you can see what I'm doing, but you can compact it into the short way if you want, but just so you can see what's going on here. And go ahead and write it the long way. So this says 46.2 centimeters cubed. And if we want to convert this into meters cubed, we need to know again how many centimeters are in 1 meter. So we got 1 meter is 100 centimeters, which is just 10 squared. I'll leave it like that. Again, just because of the scientific notation at the end. And notice that only cancels out one of the centimeters, right? We have 3 on the top, so we need to keep on doing this so that we end up with 3 on the bottom. And then times 1 meter over 10 squared centimeters equals. And then now we can go ahead and cancel things out. So the centimeters cubed cancels out with centimeters, all of them cancel out. And then now we have 4.6, I'm sorry, keep writing that, 46.2 times, and then let's look at the tens here. We have a 10 squared, a 10 squared, and a 10 squared. So what in the world does that mean? Well, we can use our exponent rules. We have the same base, so we can add up the exponents. So this turns into 10, 2, 3, 4, 5, 10 to the negative 6. Again, negative 6 because the 10 squareds are in the denominator. So if you write them on the top, they have to look like that. And then meters cubed. Okay. And then this is not in proper scientific notation, so we still have to move the decimal here. So we're going from right to left. That's 4.62 times 10 to the, now we're increasing, we're going right to left, so we're going to be increasing the exponent by 1, so that becomes negative 5 meters cubed. So negative 6 plus 1 is negative 5. And we can box that in here. Alright. Okay, so let me change the focus, adjust the focus in here. Looks better. Alright, anyway. So that one was 5, now we can go ahead and do number 6. Again, this one involves multiple dimensions. You've got to be careful here. So we're going from 12 kilograms per liter. So I'll put the L there for liters. We want to go from kilograms per liter to grams per milliliter. So here you got to choose which one you want to work with first. I'll go ahead and convert the kilograms first. You can convert the liters if you want, but I'll just do kilo. The choice is arbitrary. You can pick whichever one. There really isn't one that would make the whole process easier. It's just a matter of picking, right? So I'll do kilograms. We want to go from kilograms to grams, so that means we want to write kilograms here, grams on the top, and then we know how many grams in 1 kilogram. 1,000. That's per kilogram. And then this cancels out the kilograms. And now we're in grams, so we're good for the mass part. Now we need to do the volume part. So times, and then we want to go to milliliters. So this time I want liters on the top, and then milliliters on the bottom. And how many milliliters do we have in a liter? 1,000. So 1,000 milliliters per 1 liter. And I'm being a little sloppy here. I should be writing this using our exponents so that things simplify nicely. So again, 1,000 would be 10 times 10 times 10, so 10 cubed. And then likewise at the bottom here, this is 10 times 10 times 10, so that's 10 cubed. You don't have to write that, because these are going to cancel out anyway, but if you want to, you can go ahead and use our exponent just to be consistent. Anyway, so what happens here is the 10 cubed in the top actually cancels out with a 10 cubed at the bottom. So that's kind of cool, right? And then the liters cancels out with the liters, and then we're left with 12 grams per milliliter. Now this might be a little bit puzzling at first, because you're wondering, hey, like what happened here? We started out with 12 kilograms per liter, and then we ended up with 12 grams per milliliter. Well, that's perfectly fine. The reason why this happened is because the kilograms to grams, we in a sense scaled it down by 1,000, right? Because there were 1,000 grams in a kilogram. So in a sense, the top got scaled down by 1,000, and the bottom went from liters to milliliters. So the denominator was also scaled down by 1,000. So that means that the result is the same in terms of the number here. So it's still 12. So just changing both of the units here cancel each other out. So we just basically ended up with grams per milliliter, and we still have a 12 there. This one you don't have to write in scientific notation. It's a pretty small number, so you don't have to write 100 zeros or anything like that. So this one's okay. It's nice to keep like that. Then we have percent error. So remember, percent error is the absolute value, and this is the experimental minus the accepted. Sometimes they call it the theoretical or the accepted, and then divided by the accepted or the theoretical, however you want to define or name it. It refers to the same thing. Okay, so here we have a lab group determined that the experimental density of gold is 18.9 grams per centimeter cubed. So that's our experimental, so let me write that here. 18.9 grams per centimeter cubed. And then the actual density is 19.3, so minus 19.3 grams per centimeter cubed. And inside the absolute value bars. Whoops, can't see that. Then this is divided by the accepted, which is the actual, and we'd say the actual density. That's 19.3 grams per centimeter cubed. And then we can go ahead and simplify this. So let's go check. So let's see what we get here. 18.9. Okay, so I got 0.4 in the numerator, and in the denominator we have 19.3. And then 0.4 divided by 19.3 gives me, so this is approximately 0.020725. And then remember, this is a decimal. We're going to want to write this as a percentage. So we move this twice, we end up with 2%. So our percent error is 2%.